There's this crazy probability hack that if you stack a bunch of events together, having all of them be true at once becomes multiplicatively less and less likely. Rolling a 6 isn't anything too unordinary. However, rolling 5 of the same number, that's Yahtzee. I mean, pretty rare, right? Well, that's only true if you're rolling 5 dice. Where this gets dicey is when you're looking for a 5 of a kind with more dice, like maybe 25. All of a sudden, a 5 of a kind is all but guaranteed, as not having a 5 of a kind means having at most 4 of each. This is a trap, of course. I took something that was rare only to quickly swap it out with an entirely guaranteed one. Let me try something else. You're rolling 6-sided dice. When should you expect to roll your first 6? Well, let's see. There are 6 possible rolls, so you'd expect to get your 6 in 6 rolls, right? Yeah, not quite. The first roll is actually the best time to get the first 6. For the second roll to be the first 6, the first one needs to not be 6. So each roll becomes progressively less and less likely to be the first time you roll a 6. But okay, that was a little unfair again. I misled you with the wording of the question. But certainly, you're most likely to get exactly 1 6 with the 6 rolls, right? Once again, not quite. It's tied with 5, as the loss of opportunity to get a 6 is balanced out with the cost of being able to get more than just 1 6. Of course, these are traps. Probability is a goldmine for traps. That's why you need numbers and math to save you from all your oversights. At least that's what some people might think. But in my opinion, that's a part of the problem with probability. The fact that probabilistic thinking requires numbers means that without the numbers, it's easy to be misled and forget about the mathematical tools you can use. And even with the numbers, it's easy to get trapped because there's not much intuition. Like, what is 3.25%? Nobody knows what 3.25% is. 13 out of 400. Okay, but that's something you shouldn't be expected to know. Not to mention that numbers can and will be misleading. I mean, the difference between 3.25% and 4% seems negligible, but if you turn it to fractions, it's 1 in 25 compared to 1 in more than 33. Sure, the numbers are small, but if you compare how long it takes to double your money with these increases, one takes about 17 and 2/3 years, while the other is 21 and 2/3. There's really no winning here. Each metric looks slightly different, and that makes more to have to understand. Probability is by no means easy, but surely we can do better. Surely there's some intuition that gives a framework for how to approach probability. One of the immediate challenges with probability is how we define it. When I took my college course for probability, we needed to introduce definitions for things like sample space, events, and probability measure. And then to actually introduce a few examples, we needed to have definitions for how to set them up. Surely it should be simpler. I mean, there's the obvious intuitive idea to probability, where probability is about chance. You take a particular outcome and divide by total outcomes. But this isn't as simple as it looks. What are you counting when it comes to particular outcome and total? Formalizing this is a pain, which is why the tools we have are vague definitions and then even more definitions as we go into examples. So why can't probability be easier? Heck, why can't math be easier? And well, maybe it should be. You probably know 1 plus 1 is 2, 2 plus 2 is 4. These problems are fairly easy, but if you add more digits, 357,896 plus 98,538 is a little harder, and multiplying them is another level of difficulty. But if you know how to multiply and add, you can have a decent feel for how big these numbers are. 6 digits times 5 digits should be somewhere around 11 digits. With some intuitive understanding, there's some direction to follow. But better intuition doesn't just require understanding what multiplication is, you need some estimation and experience. You need to see the probability traps to understand why they exist, but the traps aren't anything to move on from and forget. They need to be part of the standard story in probability. So I guess the next question to ask is, where do we start in the story of probability? And after that, where do we go?